This video is going to be about the binomial distribution, but it's going to be our second take at it. Now that we have a few more tools under our belt, specifically some means of counting things, we can look at the density function itself and see that there is some intuition behind it. So that's what we'll start with. We will then refine the statement, density is not equal to probability. There's a little bit more nuance to it that I will help you all see. And then we'll take a second closer look at our DNA matching example from the FBI trying to match two individuals' DNA across 13 nucleotides. So let's just dive in. Yeah, save that. Give me a new one. And let's save it. Okay, here we go. Okay, so if you recall, the binomial distribution is the sum of some k independent Bernoulli distributions with a parameter p. So all the Bernoulli distributions have that same parameter p. We have added this word now, independent, which tells us that we can multiply k, let's say up to k p's together. And remember, p is the probability of observing a 1 from any individual Bernoulli. So suppose we are looking at a binomial that consists of the sum of 4 Bernoullis of they could be fair, they could be unfair coins. So if we consider the case of x equal to 2, then what we're looking at is 4 positions where we observe 1s or 0s. And the sum of those happens to be equal to 2. Okay, so that's one binomial observation, x equals to 2, which is the sum of 4 Bernoullis. Now the catch is, the probability that we observe 1 is p. The probability we observe 0 is 1 minus p. So if we want to consider the probability that we observed this sequence of 1s and 0s, because they are independent, we can multiply these together. And that turns out to equal p squared times 1 minus p squared. If you just rearrange the probabilities, which based on multiplication, you can happily multiply in any order you want. But I want you to notice that 1, 0, 1, 0 is just one of the many ways we could observe x equals to 2. We could similarly observe 1, 1, 0, 0. Now look, the sum of these 4 Bernoullis is still the one binomial x equals to 2. What's even trickier to see is that the probability of this sequence of 1s and 0s is still p squared times 1 minus p squared. So what we need to recognize is for the binomial observation x equals to 2, there is in fact 4 choose 2 ways to get 2 1s in 4 positions. that is k equal to 4. There is 4 choose 2 ways to observe x equals to 2, each of which has the same probability, p to the second times 1 minus p to the second. Okay, this is going to be the start to our intuition for the density function for the binomial. Let's save that. Okay, so let's suppose we're working with a binomial KP distribution. Then for x equals to 2, we have the probability of any individual sequence of 1s and 0s equal to p to the second, because we only saw 2 1s, and each 1 has a probability of p, and we can multiply those together because they're independent, times 1 minus p. Well, look, if there's k total positions, and 2 of them are filled with p, then the other k minus 2 have 1 minus p. And there are, in fact, k choose 2 ways to observe 2 1s in k positions. Okay, so let's generalize that then just a little bit. For x, whatever x might be, it could be any integer 0 to k. There are k choose x ways to observe x 1s. Since we got x 1s, we have p to the x, and then 1 minus p to the k minus x. And in fact, this is the density function for the binomial distribution written out generally in terms of k and p for whatever integer k is and whatever probability we have of the underlying Bernoulli. So this is the most general density function for the binomial distribution. In R, this corresponds to d binom. So in R, there is a function named d binom that is the density function of the binomial distribution, and it does this calculation for you for any k, p, and x. Okay, so let's move on to refine the statement. Density not equal to probability. So we should note right up front that I haven't completely lied to you. True, this statement is true for continuous distributions. We drew pictures to represent that, so I won't rehash it here again. But, and here's how we're going to modify this. For discrete distributions, I'm going to leave a space there. Density, leave a space, equals probability. I'm going to leave a space and put a period here. And I mean to read this from the right down to here. Okay. So we're going to leave some spaces in here because there's some nuance. So we'll remind you that in general, probability is area under a density function, and that remains true. But there's some nuance to the case for discrete distributions. So let's try a simple example that should highlight all the nuance we need. Consider a sample space consisting of the integers 1 through 4 and a set A consisting just of a single point. It doesn't really matter which point you choose. You just need to pick a single point. I'm just going to choose A equal to the single element 2. I'm going to make up some probabilities here so that they will be non-uniform. So this is some unknown, unnamed distribution defined over the sample space of the integers 1 through 4. And I'm interested in calculating the probability of the set A. Well, probabilities in general are expectations of indicator functions on the set over which the probability is to be calculated. For a discrete distribution such as this one, this expectation is the sum over all the x's in the sample space. There's only 4 of those possible values. And we evaluate the indicator function defined on the set A times the density function, which I haven't written out numbers for, but I'm just drawing as a picture over here. So look, there are 4 terms in this sum for each element x in the sample space, 1, 2, 3, and 4. But the indicator function only indicates the value 1 for the element 2, since 2 is the only element in the set A. For all other elements, 1, 3, and 4, the indicator function is 0, and 0 times this density function is 0. So in fact, this entire sum just boils down to f at 2. And now if you just connect the left-hand side to the right-hand side, you do indeed see that probability is equal to the density function. However, there's some catches here. It only works for discrete distributions. So we're going to say for discrete distributions only, density at a point is equal to probability of a set with only that one point in it. And by that I mean your set A, for which you want the probability, has to consist of one element. That one element happens to be the one point at which you're going to calculate the density function. So in that case, the probability is the area under the function at the point 2. That is some nuance right there. And as long as that holds, then you can say density is equal to probability. But I hope you see that the general takeaway is density is not equal to probability, unless you're in this very specific case. Okay, we're really moving up to some refined statements in the world of statistics. This is excellent. Let's see if we can apply those to our DNA matching example. So if you recall, this is the blog post on the website Freakonomics that tells us about the story of the state crime lab analyst, Catherine Troyer, who is trying to match 2 felons' DNA at 13 locations. Okay, so that's almost all the information we need. The only other information we need is for this post, they assumed that any 2 individual positions in a DNA strand consisting of 13 total positions will match with a probability of 7.5%. So in the world of probability then, what we have is a binomial distribution with k equals to 13 and p equal to 0.075. So what they're interested in is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, okay, 13. They're interested in like some number of these positions matching across two potential felons. So when some positions match, we'll mark them a 1, and when they don't, we'll mark them a 0. And they're specifically interested in 9 positions matching. So we would write that out in terms of a density function for a binomial distribution as such. Now that turns out to be this nasty expression. Which nobody really wants to do by hand. You certainly could, but we're going to turn to our friend R to do the calculation ourselves. So it turns out d binom is the function we want, and the arguments go like this. 9 is x, size is k, and probability is the probability p we have. So there is the probability of interest from the example they have in the blog post. Now what we're going to do to expand on that is to remind you that probability is area under the curve. So if we have a binomial distribution, and this goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. You got to remember that 0 is included on the binomial distribution because there could be 0 positions in the DNA sequence that match. So this is a graphical representation of the binomial distribution with 13, k equal to 13 and p equal to 0.75. Now, I'm not going to be able to draw this out super accurately, to be honest. It's going to look something like this. Maybe. We can do it in R in a second, but what I want to give you is a little bit more detail in the drawing. Now, what we looked at originally was just this probability, which happened to be some small number. But what might be more interesting is the probability that 2 individuals' DNA across 13 positions match at 9 or more. So now what I'm doing is turning my probability into a set that consists of 9, 10, 11, 12, or 13. And in this case, we're going to sum up across X in the set 9, 10, 11, 12, or 13, and F in X. You'll notice for convenience sake, I've gotten rid of the indicator function and just represented the sum, not over the entire sample space, but just over the elements in the set for which we're looking for the probability. This turns out to be kind of a headache to calculate by hand, but that's why we are using R. So let me show you some tricks here. D binom at 10, 13, and 0.075 looks like that. But we can actually ask D binom to evaluate across a vector, say the integers 9 to 10. Realistically, what we want are the D binom evaluated across the vector 9 to 13 and then we want to sum up those probabilities. Indeed, this is the probability that we have two individuals whose DNA match at 9 or more positions out of 13 possible positions. This gives us a little bit more weight to whether or not two individuals' DNA match. And this calculation is pretty simple in R, I hope you will come to believe. And if you don't believe me, I encourage you to try to write this out mathematically, what it looks like, to see how helpful R is in this case. So this was our next introduction to the binomial distribution. We got a little bit more deeper into the details of the binomial distribution, and then we looked at how R itself can help us calculate probabilities using the tools built into R.